Let's revise 10th Standard ICSE Physics Chapter 2. Now Part C, Conservation of Energy. The law of conservation of energy states that the total amount of energy in the universe remains constant. Energy can neither be created nor destroyed. Well, actually, the total amount of mass plus energy is constant, but you get the point, because mass and energy are interchangeable. But now we are going to talk about conservation of mechanical energy. That is, the total amount of kinetic and potential energy of an object remains constant. But this is true only if there is no loss of energy to the environment or to the atmosphere. So this would be true only in a vacuum, where there is no friction, which is ideally not possible. But mathematically, let's prove this by considering an object at height h and at point A. When we release it due to acceleration due to gravity, its velocity keeps on increasing. At B, which is not the midpoint of the journey, it has covered a distance of x. So now its height is simply h minus x. And in the end, it touches the ground at point C. Now we have to prove that the total mechanical energy, that is potential energy plus kinetic energy, at points A, B and C is the same. Let's start at point A. Here the initial velocity is 0, so the kinetic energy is 0, and the potential energy is maximum, which is mgh. Now at point B, let's calculate the kinetic energy. First of all, according to the equation v square is equal to u square plus 2as, u is 0 because the initial velocity was 0. The acceleration is nothing but g. It is positive acceleration, so no need to put a minus sign here. And the displacement or the distance traveled is x. Now, the formula for kinetic energy is half mv square. So, if you substitute the value of v square out here, 2gx, and 2 and 2 get cancelled, so you are left with mgx as the kinetic energy. The potential energy at B will be less than the potential energy at A. Here it was mgh, but the potential energy got used up here, which is equal to mgx. So, it will be mgh minus mgx, which on addition gives you mgh. So the total mechanical energy is conserved. It is the same. In fact, the potential energy which was lost is actually getting converted into kinetic energy. So if the kinetic energy here was 0 and potential energy was, let's say, 70 joules, and here if the potential energy is 40 joules, that means the kinetic energy is 30 joules. So the total is always a constant. Here we are assuming that there is no loss of energy. What about just as it touches the ground? So here at point C, we notice that the potential energy is 0 because the height is 0. And the kinetic energy can be similarly calculated. V square is equal to 2gh because the total distance traveled is h. Substituting that, 2 and 2 gets cancelled, so the kinetic energy is equal to mgh and the total is mgh. So interestingly, the kinetic energy at the bottom is always equal to the potential energy at the top. Remember this. So this proves the law of conservation, or rather the principle of conservation of mechanical energy. Now, let's understand the motion of the object from point A to B to C with the help of this graph. At point A, if you remember, the kinetic energy was 0, but as it moved to point C, we see that the kinetic energy is increasing and it becomes maximum at point C, where it was touching the ground. On the other hand, the potential energy at point A, the highest point, was maximum, and it started decreasing, and at the bottom, at point C, it became 0. But at each point, the total is always constant, and the total mechanical energy is always equal to mgh. At half the height, the potential energy will be half mgh, and kinetic energy will also be half mgh, but the total will be mgh. Now, let's apply this conservation of mechanical energy in a pendulum. At the extreme position, the bob is at a particular height. Let's say h. We consider the mean position as height 0. So the bob at the extreme position has some potential energy, which is mgh, and initially it is at rest, or every time it reaches the extreme position, it is at rest for that fraction of a second. So the kinetic energy is 0. When you release the bob, it accelerates and its velocity is maximum at the mean position. And then it decelerates and stops temporarily at the other extreme position. So here at the mean position, its potential energy is 0 because its height is considered to be 0. And the kinetic energy is mgh because we just saw that the kinetic energy at the bottom is equal to the potential energy at the top. So the potential energy got converted into kinetic energy. And then further, this kinetic energy, due to inertia, it will continue moving, and the kinetic energy will get converted into potential energy till the conversion is complete at the other extreme. So we now know that the potential energy at the mean position is equal to the kinetic energy at the mean position is equal to the potential energy at the extreme position. So using the formulae, we can derive the equation for V. So this is the equation which can help us to calculate the maximum velocity of a pendulum at the mean position.
According to the principle of conservation of energy, energy can neither be created nor destroyed. It only changes from one form to another. But in nuclear reactions, energy can be created from mass, and mass can be converted into energy. But that is outside the purview of our chapter. Cancel these brackets. Now, when we talk about conservation of mechanical energy, we say that the total potential plus kinetic energy is always a constant in a closed system, for example, a freely falling body, but that is only in vacuum or only when there is no friction. Now let's have a theoretical verification for this. Imagine that an object at point A is released. It reaches some point B, which is not the midpoint, and then finally reaches the Earth at point C. Initially, it was at a height h. The displacement from A to B is x, so the height of B from the ground is h minus x. Let's calculate the total kinetic and potential energy at each point. And if we can prove that it is equal at A, B, and C, then it becomes obvious that the total mechanical energy is conserved. It's a free fall, that is, there is no friction due to air here. Now, at height h, the potential energy is always mgh, and it is at rest. So the kinetic energy is 0. So the total is mgh plus 0, which is mgh. Total mechanical energy is mgh. That's at point A. Of course, you should always introduce the variables in the beginning. At point B, first of all, v square is equal to u square plus 2as. Now, at point B, the initial velocity was 0 at A. And the displacement is x because it travels x distance. And the acceleration due to gravity is g. It's positive because it is downwards. So that's 2gx. Now we know that kinetic energy is half mv squared. We substitute the value of v as 2gx. And 2 and 2 gets cancelled. By the way, it's not v, it's v squared. There's no square required here. So 2 and 2 gets cancelled, and I'm getting mgx as the kinetic energy. Now, potential energy is always mgh, but the height at point B is h minus x. So if I substitute that value, I'm getting potential energy as mg h minus x. So this is the kinetic energy, this is the potential energy at point B. Add them up, open the brackets. This becomes mgh minus mgx, mgx cancelled. What is left? Mgh. So we have proved that the total mechanical energy even at point B is mgh. Now let's do the same thing for C. Again, v square is equal to u square plus 2as. Initial velocity at A was 0. A is g, it's positive. Displacement now, total displacement is h. So that's what is written here. So the v square is 2gh. Substitute that for v squared. And 2 and 2 gets cancelled. Kinetic energy is equal to mgh, which makes sense. The total potential energy on top is always equal to the total kinetic energy at the bottom. And because the entire potential energy got converted into kinetic energy by the time it reached the bottom. The potential energy at the bottom is obviously 0 because the height is 0. So if you add them up, once again, the total mechanical energy is mgh, hence proved. Now, if you draw a graph, we notice that as you raise an object from C to B to A on top, the potential energy increases, but the kinetic energy decreases. So at the bottom, the kinetic energy was maximum at point C, but at point A on top, it was at rest, so kinetic energy was 0. Notice that if the midpoint is considered as B, where height is half of the original height, then both kinetic energy and potential energy will be equal. If I total them, the total energy is always mgh. This is the total mechanical energy which is conserved. It is the same whether it is point A, B, or C. Also notice that the kinetic energy at the bottom is equal to the potential energy on top, which means if I cut m and 2 goes up and square becomes square root, I am getting an equation that the final velocity of the object when it reaches the earth is equal to square root of 2gh. Or if the ball is being thrown upwards, then I can say that the initial velocity with which it was thrown up is equal to square root of 2gh. Mark this table as read so that it won't be tested in exam, but the graph and the note has to be studied. And finally, we come to motion of a simple pendulum. Notice that at the main position, its potential energy is 0. Yeah, it is not touching the ground, but we consider it, assume it to be 0. But its kinetic energy will be maximum. We'll calculate that soon. Now, if I lift it to an extreme point B or C for that matter, now it has some potential energy because it is at a height from the main position. And that potential energy is mgh. Now, initially, the velocity is 0, so kinetic energy is 0. The total is mgh, mechanical energy. When I release it, the potential energy is getting converted to kinetic energy. At point A, the entire potential energy would have converted into kinetic energy. So that's why the kinetic energy at A is equal to the potential energy at B, which is mgh. Total is, of course, mgh. Total mechanical energy is conserved because, again, we are assuming that it is happening in vacuum. There is no friction or loss of energy. Then again, it continues its motion due to inertia and reaches the other extreme position C. This time again, the kinetic energy starts reconverting into potential energy, and then maximum potential energy is reached at point C again, which is mgh, and kinetic energy becomes 0 once again because it comes to a stop for a fraction of a second. And when velocity is 0, kinetic energy is 0. Total mechanical energy is mgh, and once again, the total mechanical energy is conserved even at point C. And this goes on. But kinetic energy at point A was also given as half mv squared. So if I equate it like this, I can again find the velocity. The maximum velocity at the main position is square root of 2gh, where h is the maximum displacement, or the height rather. Not the maximum displacement from main position, that's the amplitude. No, the height at the extreme position. Cancel this part and this part, and even this part.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.